Hello, YouTube. So today I'm going to talk about partitions in number theory and how it is connected with statistical physics. So first, let me define what is a partition. So, so a partition is the number of ways that you can write an integer as a sum of positive integers uniquely. So let me give you an example. So So the partition of 1 is actually 1. So can because 1 can be written only one time in a one unique way. Okay, so that's why P of 1, partition of 1 will give me 1. What is the partition of 2? So 2 can be written in two different ways uniquely. One is 1 plus 1, another one is 2. So partition of 2 will give me 2. Let's see 3. So 3 can be written in three different ways. So one is 1 plus 1 plus 1. Another one is 2 plus 1. Or you can also write 1 plus 2. But we are taking this to be same. 1 plus 2 and 2 plus 1. We are taking this to be same. And then 3. So then partition of 3 will give me 3. For 4, this becomes 1 plus 1 plus 1 plus 1. And then 2 plus 2. And then 3 plus 1. And then 2 plus 1 plus 1. And then 4. So in total, how many? 1, 2, 3, 4, 5. So there are 5 ways. But this problem soon becomes very difficult. I will say try it for yourself. Try to find the partition of say 5, 6, 7, and so on. Soon you will find it is very difficult to find the number of ways. These numbers, the partitions, increase very rapidly. So it's very hard to do that. But uh, but okay, so how can I solve this? So initially I was trying to think in combinatorial way, like suppose I have 4. So 4 can be written as 1, 2, 3, 4. And then how many ways I can give this partition? So I can divide 4 as 4 and 1 and 3, or like 2 and 2, and so on. But using combinatorial way, it was difficult for me at least. I don't know. Maybe somebody can find it. But okay. But this is difficult in this way. At least what I found. So then actually I tried to soon I realized that this problem can be mapped to a problem in physics, in a specifically in statistical physics, that is very easy to solve. Okay. So let us see how. So okay. Okay. So you must have heard, if you have studied quantum mechanics, QM1, so you must have heard that there are two kinds of particles. One is bosons, another one is fermions. Okay. So in the case of bosons, these bosons are, uh, I mean, if you exchange the if you have two bosons and you exchange them, there is no change in their wave function. But if you have fermions, two fermions, and you exchange them, there is a negative sign. Okay, those are technical details, not required for now. But let's see how this can be done. So suppose I will give first try to give you an intuition of how you can map this problem of partitions into a quantum mechanic problem. So see, suppose for the partition of 2, there were two ways, right? One was 2 and one was 1 plus 1. So there is another way to write it. So this can be written as, suppose I label some states. Suppose this is state 1, state 2, state 3, state 4, and so on. Okay. And then suppose this is 2. So 2 times there is only one 2. I mean, what is the count of 2? The count of 2 is only 1. So then I will write only 1 here. Okay. And then this can be written as somewhat like, suppose this is 1, 2, 3, 4, and so on. So then I will write this term as two ones, right? Let's see another example. Suppose I have 3. So 3 can be written in three different ways. One is 3, one is 1 plus 1 plus 1 is 2 plus 1. So then again, if I label some states like 1, 2, 3, 4, 5, and so on, then I can soon see that these 3 can be written as only 1. This can be written as somewhat like 1, 2, 3, 4, 5, 3. And then this can be written as 1, 2, 2, 3, 4, 5. This can be written as 2. I have only how many 2's? Only 1, 2. 1, 2 is 1, and then 1, 1 here, right? So soon you will realize, soon you will realize that if you assume that these states are the energy eigenstates of some system, so of some imaginary system, okay, and then these are the occupancy numbers, like suppose I can say for the state, suppose I have for these states, take this example, so on, or I will say there are three particles in state 1 with the energy uh, of eigenvalue of say 3 1. So since a state since a state can be filled with more than one particle, so that means my system can be actually mapped to bosonic system, as you might have known. But this is a basic fact in quantum mechanics that boson many bosons can sit at the same location or same energy state. Okay, but for in the case of fermions have very like they repel each other. If two fermions cannot have the same exact quantum mechanical state. But in the case of bosons, this doesn't happen. So then I can map this problem of partitions. I have already mapped this problem of partition into quantum mechanical occupancy number problem. So then, since I have a bosonic system, so then I will try to write the partition function. Okay. So let's try to write the partition function. But here you will realize I need to write the grand canonical ensemble because there can be many particles. The number of particles is not fixed. The energy is not fixed. Okay. So then I need to write in terms of grand canonical partition function. Okay. So let us try to write the grand canonical partition function. Let's call this gamma or whatever. I don't know the name of this symbol. Whatever. This is not important. So then I will write lambda. Sorry, there is write 1 plus lambda to the power 1 and then e to the power minus beta e1 plus e to the power minus beta e2 plus e to the power minus beta e3 and so on. This is only one particle step because this is the chemical potential term. This one is the chemical potential term. Like basically lambda equals to the power beta mu, right? And then I will write two particle states. So two particle states. Two particle states can be written as e to the power minus 2 beta E1 plus e to the power minus beta, E1 plus E2, all possible combinations will be there, and so on, of having two particles. So here only one particle was filling the system. So initially, suppose I have these states and I have only one particle, and then this particle can sit here or either here or here or here and so on. So this one particle state will give rise to this term. Then I will have two particle states. So two particles can either sit on this or this and so on. Many combinations will be there. So this is something like this. Then I can write the three particle state minus 3 beta E1 plus minus 2 beta E1 minus beta E2 and so on and so on and so forth. I can write all the functions. Then what I can do, I can just do a simple algebraic manipulation. You can try it yourself. So suppose this is very easy to do. So suppose you choose x equals to the power minus beta E1, y equals to the power minus beta E2, z equals to the power minus beta E3, and then a equals to minus beta E4 and so on, labels sets. And then you will see that this can be written as 1 plus lambda x plus lambda square x square plus lambda cube x cube and so on. These are math, don't worry. But the main thing to realize is that, okay, let me simplify. I think this is getting very tricky or mathematically you don't get the feeling of it. Okay. So suppose I can always choose a system for which lambda equals to 1. This is in my hands. Suppose I take photons. For photons, mu equals to 0, and then e to the power beta mu will give me 1, that is basically lambda. So lambda equals to 1. And then I try to write the grand canonical partition function. So I just add this one. It doesn't matter. Little bit 1, and then I will add the terms e to the power minus beta of E1. Only one photon sitting on the E1 energy state, and then only one photon sitting on E2 energy state, then one photon sitting on E3 energy state, and so on and so forth. And then similarly, I can write the two particle states. So 2 beta E1, two photons sitting on the first energy state, and then beta E1 plus E2, one sitting on the first energy state, other photon sitting on the second energy state, and so on and so forth. And then I can write the three particle uh, contributions similar way and so forth. I can write all the different types of contributions, right? And you will see what is magical thing is happening. Not magical, it's straightforward. What when I first initially saw this, it was very magical for me. So all these E1 in this state, suppose I choose E1 to D1, E2 to D2, E3 to D3, then basically EK to VK, right? I choose this. So then in my system I will have 1 minus beta minus 2 beta minus 3 beta and so on. And then here we will have minus 2 beta minus beta 1 plus 2 that is 3 and so on and so forth. Here you will see that all the partitions for a specific energy state minus beta then this beta, this moves 2 beta minus 2 beta, and then this one, and then with the other term because then I will have three particle states, u beta, so on and so forth. Soon you will see. Just try to think. Just think it for yourself. Why this is the case? You will see that the partition function is actually the generating function of the partitions. So basically, what I have is some grand canonical partition function. This can be written as in this form. One minus beta k. K is basically one to infinity, right? And then let's explain this. So as you will explain this, you will see you are having all the partitions of every numbers of every integers 0 to infinity. P of n is basically the partitions. Partitions of the integer n. See, so quantum mechanics or in nature, since this is a photon gas, so that means in black hole radiation, somehow this can relate to black hole radiations. In this exact case, because this is photon gas, so then you will see that black hole radiations has already solved the problem of partitions. The partitions was historically very important or very challenging problem to solve, but Ramanujan actually figured it out. Asymptotic, he found asymptotic form for the number of partitions. But I think this can be actually mapped. If we can somehow do a Laplace transform of this equation, then we will obtain the Ramanujan's formula of the asymptotic formula for the partitions. Anyway, maybe that will be a video for some other time. Let's stop it now. I hope you have enjoyed this video. So I know that this video might be a bit confusing initially, but the main idea is that the problem of partitions can be mapped to a bosonic system and realize that the number of ways that you are writing a partition can be actually uh, written or mapped in terms of occupation number representation in quantum mechanics representation. So once you do that, and the other thing, this maths will flow naturally. So it's nothing out of the world. But this mapping is very interesting to do. But so just try to think it yourself, and you will. I think I know that you will love it when you finally understand it. So yeah, I hope I am able to inspire you, and I hope I am able to tell you something new. But anyways, okay. Thanks for watching this video. Goodbye.